Good afternoon. Welcome to session 4 of the A2 chemistry. We're going to be looking at some more of the Unit 4 organic chemistry today. This PowerPoint and this presentation will be made available for you through e-sgol. So if I go through some slides a little bit too quickly, you'll be able to get the PowerPoint and the presentation and go through it at your own time. Today, we're going to be looking at reactions of some alcohols, aldehydes and ketones, carboxylic acid derivatives, and if we have time, we'll look at the amines. If not, there are some notes at the end of the presentation for you to look at in your own time. We will also look at some two-step, multi-step organic sequences through some assessment questions towards the end of this presentation today. Spotting functional groups. In assessment questions, especially with the WJC, they like to give organic compounds which are multi-complicated, like this one, aspartame. And what happens is the key here is being able to identify functional groups. Therefore, you can answer questions later about how those functional groups react in certain conditions. So in aspartame, which is an artificial sweetener, it's about 200 times sweeter than sugar, we have various functional groups, which I'm highlighting for you. And we'll go through them. Got a carboxylic acid group, C double bond OOH. We have an amine, an NH2 group. We have an amide, C double bond O bonded, carbon bonded to the nitrogen. We've got an ester group, and we've got a phenol group. So in assessment questions, they give you an organic compound which you may not seen before, but you have to apply your knowledge. And we're going to look at some reactions of some of these functional groups and then put them together and see how we can do multi-step sequences with them. We're going to look at alcohols first of all. This is a little, go through this fairly quickly. This is kind of refresh what you did in year 12. Got primary group, primary alcohols. They have one R group attached to the carbon, the R group being an alkyl or an aryl group. Secondary alcohols, you have two R groups attached to the carbon. And tertiary alcohols, where you have three R groups attached to the carbon. In primary alcohols, there are two hydrogens attached to the carbon. That's key to remember that. Secondary alcohols, one hydrogen, and in tertiary alcohols, there are no hydrogens attached to the carbon with the OH on it. Some examples of primary alcohols: phenol, ethanol, and butanol. Sorry, just get the pointer out. Butan 2-ol and 2-phenyl propan 2-ol. Here, there's one hydrogen on here, and on the tertiary, there are no hydrogens on the carbon next to the OH group. How alcohols are formed, formation of alcohols. Again, a little bit of feedback or revision from year 12, where you got a halogen alkane and you have a nucleophilic substitution. You have carbon and chlorine, chlorine being the more electronegative element. So we're drawing the electrons towards the chlorine, making the carbon slightly electron deficient, or delta plus and delta minus. Now, it's important that when you do your mechanisms that you include the delta plus and the delta minuses. The OH minus lone pair on the oxygen forms a bond with the carbon. The pair of electrons between the carbon and the chlorine join the chlorine atom, and you get your nucleophilic substitution, and you form ethanol and the chloride ion. You could have an example: 2-bromopropane plus potassium hydroxide gives you propan 2-ol and KBr. Now, in year 12 also, that these ions formed, the chloride ion and the bromide ions, could be further tested with acidified with nitric acid and a silver nitrate. The chloride ions would produce a white precipitate and the bromide ions would form a cream precipitate. So you could identify that a halogen alkane was present. Also from year 12, remember halogen alkanes can cause an elimination reaction with potassium hydroxide or sodium hydroxide in ethanol. The key here is that it's in ethanol, so to form an alkene. So you have an elimination reaction in those cases when the potassium hydroxide or sodium hydroxide is in the ethanol. They could be also formed by the reduction of aldehydes, ketones, or carboxylic acids. Here's some examples. Carboxylic acids, if they are reduced, will form primary alcohols. You use lithium aluminium hydride as the reducing agent. It's strong enough to reduce the carboxylic acid right back down to the primary alcohol. So propanoic acid to propanol, benzoic acid to benzyl alcohol. Aldehydes can also be reduced to primary alcohols, and ketones will be reduced to secondary alcohols using lithium aluminium hydride in ether. Because lithium aluminium hydride has to be in ether. If it's in water present, it will hydrolyze itself very quickly. Reactions of some of the alcohols. Oxidation, yet again from year 12, where you use potassium dichromate, orange in color, and it changes to green as oxidation occurs. Primary alcohols will be, first of all, be oxidized to an aldehyde. Now, if you wish to get isolate the aldehyde, first of all, there's gentle heating and aldehyde is formed, which is immediately distilled off before any further oxidation. The aldehyde would further oxidize to form carboxylic acids from a primary alcohol. Secondary alcohols will form ketones. They will not further oxidize. The secondary alcohol will form a ketone, and then there will be no further oxidation. Tertiary alcohols, there is, like in 2-methyl-propan-2-ol, tertiary alcohols cannot be oxidized as they do not have a hydrogen atom on the carbon bonded to the OH. So primary will be oxidized to aldehyde first and then to carboxylic acid, secondaries to ketones, tertiaries, no oxidation. With hydrogen halides, to produce alcohols to halogen alkanes, there are three ways that we could do this. You can pass HCl gas through alcohol with dry zinc chloride as a catalyst. You could react with phosphorus chloride, but phosphorus oxide, trichloride, and hydrogen also form, making separation of the halogen alkane form difficult if similar boiling point. The method that is favorable is using SOCl2, thionyl chloride. Products form sulfur dioxide and HCl are both gases and are released, therefore leaving halogen alkane formed. If you want to put bromine on to make a bromo alkane, you heat the mixture with KBr and 50% H2SO4 and you substitute on the OH for the Br. And for iodine, react with phosphorus iodide. These, the thionyl chloride one, the bromine one, and the iodine ones, you have to remember the reagents. Forming esters. Now this is key. A lot of assessment questions using forming of esters and isomers of esters. Carboxylic acids react with alcohols in the presence of a strong acid catalyst, sulfuric acid, to form esters and water. It's a reversible reaction. Esters have two parts in their names, e.g. methyl propionate, ethyl ethanoate. The bit ending in the ON8 comes from the carboxylic acid. The bit ending in the YL comes from the alcohol that has formed it and is next to the single bonded oxygen. Some examples. Ethyl propanoate. The ethyl bit, the bits in the red, are from the alcohol. The propanoate, okay, comes from the carboxylic acid. So propanoic acid and ethanol make ethyl propanoate. Same here. Propyl, this part here from propanol. Methanoate from methanoic acid. Methyl from methanol. Butanoic acid. Propanol, ethanoic acid. So esters have a distinct kind of sweet, fruity smell. So ester, we have this C double bond O, CO, and then alkyl group formed at the end. Here's some examples. General equation, it is eliminating water between the acid and the alcohol. The OH from the acid and the hydrogen from the alcohol, and there's water formed as well. So an example is benzoic acid and ethanol making ethyl benzoate with this ester functional group present. And classic one you may have done in practical work is ethanoic acid, ethanol making ethyl ethanoate. Alcohols with acid chlorides also make an ester, and we're going to have a look a bit more at acid chloride reactions in a few slides later on. Example, benzoyl chloride and sodium phenolate equals phenyl benzoate and sodium chloride. That's just the phenol in sodium hydroxide, and we form the ester. So alcohol plus carboxylic acid makes an ester, and an alcohol and an acid chloride also makes an ester. I showed you last week some mind maps of reactions. Here's one for alcohols. I do recommend that you try drawing and making your own mind maps of all the different reactions, with the functional group in the middle, on the left-hand side, how the alcohol is formed, and then on the right-hand side, I've drawn the reactions of, in this case, ethanol with different reagents. We'll move on to aldehydes and ketones. Aldehydes, we've got the carbonyl group, and aldehydes, the carbonyl groups, that the examples I've given you are at the end of the molecule. So the carbon with the double bond is next to a carbon bonded to a hydrogen. So we've got methanol, ethanol, propanol, and 3-methyl butanol. If you've noticed, at the end of the compound is the aldehyde group and the skeletal form representation there as well. Ketones, here we've got the carbonyl group in the middle of the molecule, surrounded the carbon has got R groups either side. So we've got propanone, butanone, pentan-3-one, and 4-methyl pentan-2-one. Oxidation reduction of carbonyls. Aldehydes can be oxidized by mild oxidizing agents to carboxylic acids, but ketones are not oxidized by these oxidizing agents, as a C-C bond would have to be broken. Aldehydes and ketones can both be reduced to alcohols, primary alcohols from aldehydes, and ketones will be reduced to secondary alcohols. So primary alcohols here can be oxidized, as we mentioned before, right through to carboxylic acid. Aldehydes can be reduced to primary alcohols. Aldehydes can be oxidized to carboxylic acid, or when we look at some of the tests for aldehydes, tolerance reagent, Phthalic solutions also oxidize the aldehyde to carboxylic acid. Ketones, secondary alcohols are oxidized to ketones. Ketones can then be reduced to secondary alcohols. I would recommend, and it's left on the resources slide at the end, experiments on film, experiment C22E, which is about planning and organizing tests for functional groups. That can be watched via the hub. (2,4-dinitrophenolhydrazine) reacts with both aldehydes and ketones. The product is an orange precipitate. So both aldehydes and ketones give an orange precipitate with 2,4-dinitrophenolhydrazine. Now, the actual precipitate can actually be filtered and recrystallized, and the melting point taken of the orange crystals produced. Now, that specific melting point will actually give you and identify the specific aldehyde or ketone by comparing it with a database. So say if you have got aldehyde or ketone, you can actually specify which aldehyde or ketone it is. So when it reacts with 2,4-dinitrophenolhydrazine, it's an addition reaction first, and then there's elimination of water, and it forms the orange precipitate. We don't need to know this mechanism, but I have seen in assessment questions this compound, and they've actually used it for nitration of benzene question, where you're adding a nitro group to the benzene ring. Tolerance reagent. Tolerance reagent could be added to both aldehydes and ketones. Only aldehydes will form a silver mirror. So before and after, you will get a silver mirror produced with an aldehyde. The tolerance reagent is ammoniacal silver nitrate, and what happens is that the silver one is reduced to silver. Phthalic solution, aldehydes give a color change blue to red. In the phthalic solution, it's a dark blue solution of copper ions made by mixing copper sulfate solution with potassium sodium tartrate and sodium hydroxide, and you can produce a copper-2 complex. The copper-2 complex is reduced yet again to copper-1, which will give you the red color, and it give you a test for aldehydes. So tolerance and phthalic solution will give positive tests for aldehydes. Ketones give no result with tolerance reagent or Phthalic solution. Aldehydes further test. The iodoform test. Test for ketone with a methyl group next to the carbonyl group. Ethanol is the only aldehyde which would give a positive test, and ethanol also will give a positive test. So methyl ketone, where the carbon is next to a CH3, the carbonyl group with the carbon on it, the CH3 group is neighboring. The organic compound is added to a mixture of iodine and dilute sodium hydroxide, or a mixture of potassium iodide and sodium chlorate. Now, what happens is you've got to recognize these, and as soon as you see this, you know that an iodoform test is being carried out. You get a formation of a solid iodoform, yellow color, which is positive test for a methyl ketone. There's your solid form, yellow form formed. Examples: propanone, methylphenyl ketone. One of the key reactions for aldehydes and ketones is nucleophilic addition. Now, we've come across different mechanisms: nucleophilic substitution, electrophilic addition, electrophilic substitution last week. Today, we're going to look at nucleophilic addition. It's a good way of extending a carbon chain and compound by reacting with potassium iodide, then acid. So I'll go through this slowly. So we're going to go through the mechanism. You've got an electron deficient carbon as is attached to the oxygen in the carbonyl group. The lone pair forms a bond to the carbon. Pair of electrons between the carbon and the oxygen is placed onto the oxygen, so it has an extra lone pair and it gets a negative charge. The nitrile group is attached and the lone pair attached to the H plus from the sulfuric acid, and you produce a hydroxynitrile. Now this nitrile is useful in extending the carbon chain. It's marked here because the carbon here has 4 different functional groups, so it can show optical isomerism. Looking at propanol and KCN, propanol and HCN, so we've got a aldehyde with HCN, hydrocyanide, and we form the hydroxynitrile. Carbon chain has been extended by 1 carbon. The mechanism as before, you've got a delta plus electrode deficient carbon, pair of electrons and cyanide attaches itself to the carbon, makes a bond, pair of electrons go to the oxygen, and then those pair of electrons join the H plus from the acid. Many hydroxynitriles contain a chiral carbon, where 4 different functional groups attached to 1 carbon. So here, now I can attack from underneath the molecule or above the molecule. It's formed as a racemic mixture. In other words, it's 50-50 mixture of the optical atomers. So what happens is they're equal molars of each optical isomers. So it forms a racemic mixture which has no effect on polarized light. Enantiomers, if there's more enantiomer than another, it will rotate polarized lights, and an indication of optical isomerism. Has equal chance of attack, as I said, from above and below the plane of the carbonyl group. Once we have the hydroxybutynitrile formed, we can acid hydrolysis of this will produce the nitrile group. The chain is extended and it could be hydrolyzed to a carboxylic acid group. Carboxylic acids and their derivatives. Examples of carboxylic acids. So we're looking at COOH, or sometimes written as CO2H group within the organic molecule. Aliphatic ones in order: methanoic, ethanoic, propanoic. There's some others, 2-methyl propanoic. Aromatic ones as well, with the attached directly to the benzene ring in this case. You can have dicarboxylic acids, which are useful in making polyesters when they react, or condensation polymerization with diols. You've got butane-dioic acid, propane-dioic acid, and 1,4-benzene dicarboxylic acid are examples. Citric acid is another example of a dicarboxylic acid. So we're going to look through briefly today some of the carboxylic acid derivatives. We have esters, acyl chlorides, amides, and acid anhydrides. Formations, we're not going to stay too long on this slide. We have oxidation, as we said, from primary alcohol for ethyl benzene, okay, for aryl, for benzene derivatives, then you use alkaline potassium permanganate. It's a stronger oxidizing agent. Okay, we have the alpha carbon there. If there's hydrogens on there, then it will be oxidized down to benzoic acid. Hydrolysis of nitriles, which we just looked at. If you have a nitrile with sulfuric acid, hydrolysis, it will make a carboxylic acid. Acidity of carboxylic acids are weak acids. They are partially dissociated, but they are strong enough to displace carbon dioxide from carbonates. And we're going to have a look at that in the next slide about testing for carboxylic acids. It's in equilibrium, okay, so it's only partially dissociated, so the equilibrium is mainly on the left-hand side. The strength of carboxylic acids, the longer the chains, the longer the alkyl group, they are electron releasing and they push electrons towards the acid ends, and increasing the chain length pushes the electron density onto the CO minus, make it more negative and less stable. This makes the acid less strong, so it doesn't dissociate as much to form the less stable ion. If you have an electron withdrawing group like chlorine, then the electron density around the CO minus is less and is more stable, okay, and therefore that the ion, once dissociation occurs, the ion is more stable, therefore the acid is stronger. As an acid, it can react with sodium hydrogen carbonate to release carbon dioxide. If you react it with sodium carbonate, it also releases carbon dioxide, which is with bases, it will form the salt. Sodium ethanoate, sodium propionate, so sodium benzoate, whatever carboxylic acid you started with. The test for carboxylic acid is fizzing with sodium hydrogen carbonate or sodium carbonate, the CO2 being released. Carboxylic acids with esters, we looked at that before. Carboxylic acid with an alcohol gives you ester plus water. As I mentioned before, you can have the reverse. Esterification can be reversed, if known as hydrolysis. It can be carried out with sodium hydroxide to form the salt and alcohol, and then acidified to get carboxylic acid, as below. So you form sodium salt, or if you do it with acid hydrolysis, you would form the acid and alcohol that you originated from. Decarboxylation of carboxylic acid is shortening the carbon chain. So you can have salts or the acid heated with soda lime. In assessments, they say soda lime, which is pure sodium hydroxide. If you notice that you form an alkane with one less carbon. So forms a simple hydrocarbon with one fewer carbon atom. In assessment questions, when you see something heated with soda lime, you realize that the decarboxylation is occurring. Salts also can be decarboxylated with heating with soda lime. Carboxylic acids to acid chlorides. Now, acid chlorides, you replace the OH in carboxylic acid with chlorine. Now, a formation of the acid chlorides can be done three ways. First method with thionyl chloride, PCl5, or third method, PCl3. Method one, as before, when we looked at alcohols turning into halogen alkanes, thionyl chloride method is preferred because sulfur dioxide and HCl is produced, which come off as gases. These other method 2 and 3 harder separation methods between the acid chlorides and the byproducts. An example there Acyl chlorides, most reactive carboxylic acid derivative. You've got two electronegative atoms attached to the carbon, so that it's easily attacked by a nucleophile, which makes the carbon algorithm more electrophilic. This makes nucleophilic attack a lot easier. Reaction with water, very reactive. Ethanol chloride reacts with water, produces a weak acid, a strong acid, and in fact the HCl can come off as fumes, turning blue litmus paper red. Reaction with alcohol to form esters. An alternative way, instead of using carboxylic acid, you can use an acid chloride with an alcohol to form the ester, but you produce HCl as well. And also, acyl chlorides can react with amines to form amides. So here we have ethanol chloride, methylamine, and you form N-methyl ethanamide and hydrochloric acid. So what happens is that you're losing HCl between the two organic molecules. Carboxylic acids to amides. We got primary amides where you have two hydrogens attached to the nitrogen. Secondary amide where you have one hydrogen, and tertiary amides, there are no hydrogens attached to the nitrogen atom. You have R groups or alkyl or aryl groups attached. How we form carboxylic acids? We react a carboxylic acid with ammonia. It forms the ammonium salt of the acid, and then you heat that and it will form the amide. So you form the salt first, heat, eliminate water, and you form the amide. Carbon, C double bond O, and NH2, benzamide. Acyl chlorides to amides. Here we have ethanol chloride and ammonia. Replace the chlorine with NH2, and ammonium chloride is also formed. Extra acid anhydrides can react with ammonia also to form the amides and also carboxylic acid. Amides can be hydrolyzed in acid, to go back to the carboxylic acid and ammonium chlorides. In alkaline conditions, they will form the salt of the acid, here in this case sodium ethanoate, and ammonia, okay, which would turn red litmus paper blue if you did this as a test, that you had an amide present. Amides hydrolyzed to acid and amine or amine salt. Nitriles with CN group, formation of, sorry, that should be formation from an amide, is that you hit it, this you have to learn, phosphorus oxide, removing H2O, removing water, you form the nitrile group, ethanitrile in this case. Formation from halogen alkanes, extending the carbon chain. This is nucleophilic substitution, and you form the nitrile. And as I mentioned before, slides 19 to 31, you have nucleophilic addition as well. Key reactions, I'm going to speed up a little bit so we can look at some of the assessment questions. Nitriles could be hydrolyzed to form the carboxylic acid. In alkaline hydrolysis, you form the carboxylic ion or the salt. Reduction of nitriles, very important to form amines. Ethanitrile form ethylamine. We've got 2-methyl-benzonitrile forming 2-methyl-benzylamine. So the carbon gets 2 hydrogens and the nitrogen gets 2 hydrogens to form the amine. Okay, let's have a look at some questions where we put a lot of those reactions and reagents together. Butylamine can be made from propan-1-ol in a 3-stage process. Give the reagent used and the structural formula of the product for each stage. So there's the question that was put in the assessment. And we'll just have a look. We start with propanol to butylamine. And what we notice between the starting and finishing compounds, it gains 1 carbon, which indicates that you've added a nitrile group. Okay, it's changed the functional group as well, and also useful. Amines are formed from nitriles. So what happens is we've got to form a nitrile in this process so that we can extend the carbon length. If we're working backwards, so the product that we're after is butylamine. We can get that formed from the butanylnitrile by reduction with lithium aluminium hydride. The nitrite can be formed from a halogen alkane. If you notice from this step to this step, we've added a carbon, KCN or HCN. The halogen alkane comes from propanol. And the preferred method is to use thionyl chloride rather than PCl5. So in the reaction we've looked at, the OH is replaced, substituted with the chlorine. So if we go back, the reagents used start off with from propanol to chloropropane, then KCN to make butanylnitrile, then the nitrile is reduced using lithium aluminium hydride to form butylamine. Octa-1N3-ol is a compound that attracts biting insects such as mosquitoes. It is contained in human breath, sweat, and is also produced by some mushrooms. As I said, in assessments, they're looking for you to apply your knowledge from new compounds that are put in the assessment question. Sorry. Quickly go through this stage. What happens is between here we're looking at the difference. Here you've gone from an alkene to an alkane and you gain a bromine. So that would suggest plus HBr. Here you've changed the bromine to an OH, which indicates a substitution reaction. From here you go from OH to carbonyl groups, which indicate oxidation process. Give the molecular formula of octa-1N3-ol. Oc, obviously there's 8 carbons. If you looked at the skeletal formation there, it has 16 and 1 oxygen. As I said, that substitution reaction in the second stage, you would use sodium hydroxide, and the type of is nucleophilic substitution. And the last stage, as I mentioned, you've gone from alcohols to carbonyl groups. You would use oxidation of using potassium dichromate, acidified potassium dichromate. An isomer of octa-1N3 was reacted with alkaline iodine and produced a yellow precipitate. The alkaline iodine indicates it's an iodoform test. So the formula of the yellow precipitate form is the iodoform CHI3. Suggests a structural formula for the isomer. Well, if it's given a positive, it needs to have a methyl ketone with the double bond O and next to a CH3 group. So the hydrogen has come off there, and you formed a double bond O at the end next to the end methyl group. Octane 2,3-diene is a pale yellow liquid, and octane 3-diol is a colourless material. Statal reagent that could be used to produce octane 2,3-diol, so the reverse of stage 3. Okay, we're looking at reduction, so you could use sodium borohydride or lithium aluminium hydride. To measure the reaction, there's a change in colour. You would use a colorimeter, which would measure the absorbance or transmittance of light through the reaction as it proceeded. I'm due to time. The answers are here for this. You can go through it in your own time and have a look at this assessment. And I've written some notes before and after with the answers. As we are coming to the end of time, I've just mentioned resources for students. e-sgol resources, this recording and further notes on this PowerPoint presentation are available. Experiments on experiment C22 and the WJC resources, revision guide and topic by blended learning. It's a bit rushed today, but thank you very much for listening. And if you download get a copy of the PowerPoint, there is more information on amines at the end. Thank you again for listening.